Today we'll be learning about atmosphere, its composition. Well, the objectives of this lesson: what is atmosphere, what is the need to study it, characteristics and the significance of terrestrial atmosphere, origin of atmosphere and composition. To begin, the atmosphere is a mixture of numerous gases. This gaseous cover of the earth is held around it by the gravitational attraction and rotates with it. Like the lithosphere and hydrosphere, the atmosphere too is an integral part of the planet Earth and is inseparable from it. However, the density of the atmosphere decreases rapidly with the altitude. About 97% of the Earth is concentrated in the lower 29 kilometers. In fact, the Earth's surface, which sets the stage for all the natural as well as human activities, may be deemed to represent the bottom of this shallow ocean of Earth. This is why it is all the time being influenced by the change occurring in the air ocean. General characteristics of the atmosphere. The atmosphere differs from lithosphere and hydrosphere in many respects. Air is a colorless, odorless and tasteless substance. Besides, it is mobile, elastic and compressible. The most interesting fact about air is that we do not feel its presence unless there is horizontal motion in it. Air in horizontal motion is known as wind. Although air is not as dense as land or water, it has weight and the pressure it exerts on the surface is called atmospheric pressure. Air pressure is the most important climatic element. The atmospheric pressure at sea level is 1034 grams per square centimeter, 14.7 pounds per square inch. Significance of the terrestrial atmosphere. All the life forms owe their existence to the atmosphere. The physiological existence of man and every other living organism depends upon the availability of water. Animals need oxygen while plants need carbon dioxide. Most living things cannot survive temperatures much warmer or colder than those found on the earth. They also cannot live long if they are exposed to a large amount of ultraviolet radiation given off by the sun. It is the atmosphere that provides most of the oxygen and carbon dioxide and maintains the requisite level of water and radiation in the Earth's system. It is the gaseous covering of the Earth which maintains the temperatures that suit us. In the absence of the atmosphere, there would have been great extremes of temperatures to the tune of 200 degrees Celsius between day and night. Situations which may have made life on Earth impossible. The atmosphere also shields us from much of the sun's ultraviolet radiation, so injurious to the plants and animals alike. It also acts as a protective wall against the bombardment of the meteors of all sizes. In short, there are few other aspects of our physical environment that influence our daily lives more than the phenomena we collectively call the weather. The currents, motions and various other activities of the atmosphere combine together to produce this weather. Clearly then, since the atmosphere affects the lives of every one of us, we must know more about it. Perhaps that is the reason why people's interest in atmosphere is probably as old as the history of mankind. All our activities are governed directly or indirectly by the conditions found in the atmosphere. All this requires a greater need for increased awareness and understanding of the Earth's atmosphere and its nature. Earth's atmosphere protects us from incoming space projectiles, comets, asteroids that burn up before reaching the planet's surface and blocks harmful short wavelength radiation from the sun. The lower boundary of the atmosphere is considered to lie on the Earth's surface. The upper boundary is the gradational transition into space. The weather we experience at the land surface is largely determined by interaction of different wavelengths of incoming solar radiation with the atmosphere. Solar radiation supplies the energy necessary for cloud formation, precipitation and local weather conditions. The relatively pleasant average global temperature of 15 degrees Celsius is a direct result of two factors. First, visible light is converted to heat when solar radiation strikes the Earth's surface. Second, the heat is trapped close to the planet's surface by the greenhouse gases, carbon dioxide, methane, nitrous oxide, water vapor, that make up just a fraction of the Earth's atmosphere. All planets have atmospheres, but the specific mix of gases in the Earth's atmosphere is termed air. Two common gases, nitrogen and oxygen, make up about 99% of the dry air. Moist air may contain up to 7% water vapor or aerosols, microscopic particles. In addition, trace amounts of other gases, carbon dioxide, methane, ozone, have proved crucial in recent discussions of global climatic issues. Water is the only naturally occurring compound that exists in three states: liquid, gaseous, solid, on the Earth's surface. Heat energy is transferred through the atmosphere as water changes from one state to another. Heat is absorbed in the processes such as melting, sublimation, and evaporation. In contrast, heat is lost to the atmosphere during the freezing, condensation, and precipitation. The presence of moisture in the atmosphere is measured by the humidity of air. Humidity and condensation are closely related, as condensation inevitably occurs when the air is saturated with moisture, 100% humidity. Air pressure decreases with the altitude and results in temperature changes as descending air is compressed or rising air expands. The section on air pressure and the condensation explains how such pressure changes can lead to condensation and cloud formation. There are a variety of mechanisms that cause air to rise, thus leading to condensation and cloud formation. The form of clouds which provide us with clues to approaching the weather systems. The section on clouds and the cloud formation discusses the lifting mechanisms that lead to cloud development and describes how we can read the sky to learn what the clouds can tell us about regional weather patterns. Weather systems are carried cross country by prevailing winds that are tied directly to regional low and high pressure systems characterized by warm, ascending, and cool descending air respectively. Pressure and wind details the relationship between the air pressure and the wind strength and direction and explores how other factors, friction, rotation of the earth, result in flow of the air into low pressure systems and high pressure systems. The natural laws that govern the interaction between temperature, pressure, and moisture in the atmosphere make it possible for meteorologists to predict short-term changes in the local weather conditions, weather forecasts. The fact that these forecasts are sometimes wrong illustrates the dynamic changes that such systems undergo during a single day and underscores the complexity of the atmospheric system. Origin of the atmosphere. We know little about the origin of our atmosphere, just as we know little about the origin of our planet. In the absence of any reliable evidence, one can only speculate. According to cosmologists, our planet most likely originated from the Sun about 4.6 billion years ago in the wake of the latest encounter with a passing star following a cosmic event popularly known as the Big Bang. After its separation from the Sun, it started revolving around the Sun under the effect of Sun's gravitational pull and rotating about its axis like a fiery ball surrounded by an extremely hot gaseous envelope which may be called the primordial atmosphere. However, it may be imagined that the primordial atmosphere at that stage must have been at a great upheaval as it hurled through space and its hot gaseous envelope rapidly cooled, condensed, and solidified, forming a solid crust in the surface levels after giving out considerable amount of volatile hot gases and vapors from the molten material at the surface. Part of the hot gases and vapors which cooled and condensed into water formed the world's oceans. The remainder formed a gaseous envelope around the planet or was stored in rocks. The atmosphere thus formed had a preponderance of hydrogen and little or no oxygen, so could not support the life of the kind that we know on the Earth today. However, as the Earth cooled down further, complex chemical actions and reactions in the crust and the interactions between the crust and the atmosphere gradually led to the formation of an atmosphere which could support an early form of life such as single-celled microbes which required little oxygen for their survival. Such microbial forms of life also known as blue-green algae, perhaps, first appeared in the oceans. There they absorbed carbon dioxide and in the presence of water and sunlight released oxygen by a biochemical process known as the green plant photosynthesis. This accumulation of the oxygen in the atmosphere facilitated the evolution of more complex and multi-celled forms of life which we observe on our planet today. It is believed that all these developments occurred within the first 1 billion years of the Earth's history, and that since then our atmosphere has gradually stabilized to its present state. Composition of the atmosphere. The atmosphere can be described as a blanket of air surrounding the Earth. This enveloping mixture of gases contains huge number of solid and liquid particles collectively called aerosols. Some of these gases may be regarded as permanent atmospheric components that remain in fixed proportions to the total gas volume. Other constituents vary in quantity from place to place and from time to time. If the suspended particles, water vapor and other variable gases were excluded from the atmosphere, we would find that the dry air is very stable all over the Earth up to an altitude of about 80 kilometers. Nitrogen and oxygen make up 99% of the clean, dry air. The remaining gases are mostly inert and constitute about 1% of the atmosphere. The deep layer through which the gaseous composition of the atmosphere is generally homogeneous is called homosphere. At the higher altitudes, the chemical constituent of the air change considerably. This layer is known as the heterosphere. Nitrogen. Nitrogen is removed from the atmosphere and is deposited at the Earth's surface mainly by the specialized nitrogen fixing bacteria and by the way of lightning through precipitation. The addition of this nitrogen to the Earth's surface, soils and various water bodies supplies much needed nutrition for the plant growth. Nitrogen returns to the atmosphere primarily through biomass combustion and denitrification. Oxygen. Oxygen is exchanged between the atmosphere and the life through the process of photosynthesis, and rephotosynthesis produces oxygen when carbon dioxide and water are chemically converted into glucose with the help of sunlight. Respiration is the opposite process of photosynthesis. In respiration, oxygen is combined with glucose to chemically release energy for metabolism. The products of this reaction are water and carbon dioxide. Water vapor. The next most abundant gas on the table is water vapor. Water vapor varies in concentration in the atmosphere both spatially and temporally. The highest concentrations of water vapor are found near the equator over the oceans and the tropical rainforests. Cold polar areas and subtropical continental deserts are locations where the volume of water vapor can approach 0%. Water vapor has several very important functional roles on our planet. Firstly, it redistributes heat energy on the Earth through latent heat energy exchange. The condensation of water vapor creates precipitation that falls to the Earth's surface, providing needed fresh water for plants and animals. Thirdly, it helps warm the Earth's atmosphere through the greenhouse effect. Carbon dioxide. The fifth most abundant gas in the atmosphere is carbon dioxide. The volume of this gas has increased by over 35% in the last 300 years. This increase is primarily due to the human-induced burning from the fossil fuels, deforestation and other forms of land use change. Carbon dioxide is an important greenhouse gas. The human-caused increase in its concentration in the atmosphere has strengthened the greenhouse gas effect and has definitely contributed to global warming over the last 100 years. Carbon dioxide is also naturally exchanged between the atmosphere and life through the process of photosynthesis and respiration. Methane. Methane is a very strong greenhouse gas. Since 1750, methane concentrations in the atmosphere have increased by more than 150%. The primary sources for the additional methane added to the atmosphere in the order of importance are rice cultivation, domestic grazing of animals, termites, landfills, coal mining, oil and gas extraction. Anaerobic conditions associated with rice paddy flooding results in the formation of methane gas. However, an accurate estimate of how much methane is being produced from rice paddies has been difficult to ascertain. More than 60% of all the rice paddies are found in India and China, where scientific data concerning emission rates are unavailable. Nevertheless, scientists believe that the contribution of rice paddies is large because this form of crop production has more than doubled since 1950. Grazing of animals releases methane to the environment as a result of herbaceous digestion. Some researchers believe the addition of the methane from this source has more than quadrupled over the last century. Termites also release methane to similar processes. Land use change in the tropics due to deforestation, ranching and farming may be causing termite numbers to expand. Nitrous oxide. The average concentration of the greenhouse gas nitrous oxide is now increasing at a rate of 0.2 to 0.3% per year. Its part in the enhancement of the greenhouse effect is minor relative to the other greenhouse gases already mentioned. However, it does have an important role in the artificial fertilization of the ecosystems. In extreme cases, this fertilization can lead to the death of forests, eutrophication of the aquatic habitats, and species exclusion. Sources for the increase of nitrous oxide in the atmosphere include land use conversion, fossil fuel combustion, biomass burning, and soil fertilization. Most of the nitrous oxide added to the atmosphere each year comes from deforestation and the conversion of forest, savanna, and grassland ecosystems into agricultural fields and range fields. Both of these processes reduce the amount of nitrogen stored in the living vegetation and soil through the decomposition of the organic matter. Nitrous oxide is also released into the atmosphere when the fossil fuels and biomass are burned. However, the combined contribution to the increase of this gas in the atmosphere is thought to be minor. The use of nitrate and ammonium fertilizers to enhance plant growth is another source of nitrous oxide. How much is released from this process has been difficult to quantify. Estimates suggest that the contribution from the source represents from 50% to 0.2% of the nitrous oxide added to the atmosphere annually. Ozone. Ozone's role in the enhancement of the greenhouse effect has been difficult to determine. Accurate measurements of the past long term, more than 25 years in the past, levels of this gas in the atmosphere are currently unavailable. Moreover, concentration of the ozone gas are found in two different regions of the Earth's atmosphere. The majority of the ozone, about 97%, is found in the atmosphere in the concentrated region of stratosphere at an altitude of 15 to 55 kilometers above the Earth's surface. The stratospheric ozone provides an important service to the life on the Earth as it absorbs harmful ultraviolet radiation. In the recent years, levels of stratospheric ozone have been decreasing due to the buildup of human-created chlorofluorocarbons. Since the late 1970s, scientists have noticed the development of severe holes in the ozone layer over Antarctica. Satellite measurements have indicated that the zone from 65 degree north to 65 degree south latitude has had a 3% decrease in the stratospheric ozone since 1978. Ozone is also highly concentrated at the Earth's surface in and around the cities. Most of this ozone is created as a byproduct of human-created photochemical smog. This buildup of the ozone is toxic to the organisms living at the Earth's surface. Dust particles. Innumerable dust particles are held in suspension in the lower layers of the atmosphere. It may be pointed out that the term dust particles includes all the solid particles present in the air, excepting the gaseous and the water vapor. There is a great variation in the amount of dust over the Earth's surface. Even over the oceans, the air contains thousands of dust particles per cubic centimeter. Many particles are invisible to the naked eye and are microscopic. They originate from different sources, both natural and man-made. They include sea salts from breaking sea waves, pollen in various organisms lifted by the wind, smoke, and soot from fires, and tiny sand particles rise from active volcanoes. These dust particles are held in air by the movements of the atmosphere. However, certain particles are too large to remain for a very long time in air. At times, the ascending air currents carry the dust particles to great heights in the atmosphere. The upper atmosphere also receives a very small amount of dust from the disintegration of the innumerable meteors passing through it. From a meteorological point of view, these tiny solid particles may be very significant. They absorb a part of incoming short-wave solar energy. Also, part of the insulation, especially the short wavelengths of blue light, is scattered by the molecules of air and fine dust. A certain percentage of solar radiant energy is reflected back by these solid particles. Dust particles, by the process of scattering, contribute to the varied colors of red and orange at the sunrise and the sunset. The blue color of the sky is also due to the selective scattering by the dust particles. Some of the dust particles are hygroscopic in character and therefore act as nuclei of combination. Thus, dust particles are a major contributory factor in the formation of clouds and fogs. The duration of dawn and twilight, as well as their intensity, are all controlled by the presence of these solid particles in air. The atmosphere is a mixture of numerous gases. This gaseous cover of the earth is held around by it by the gravitational attraction and rotates with it. Like the lithosphere and hydrosphere, the atmosphere too is an integral part of the planet Earth and is inseparable from it. Since atmosphere affects the lives of every one of us, we must know more about it.